Structural performance of glass, page 57. For typical sizes and thicknesses used in windows, curtain walls, and skylights, glass reacts to loads as a combination plate and membrane. Conventional engineering procedures for thin plates may not be applicable when the maximum lateral deflection exceeds half the glass thickness. Glass strength can only be determined by extensive testing or complex engineering analysis. So the wind load coming out of glass can't be more than half. The bow in the glass cannot be more than half the glass thickness, or it's going to break. And some of the tests that they're going to talk about right now may not pertain to thinner plates of glass. Glass is a brittle, elastic material up to the point of fracture. Its strength is controlled by the interaction of tensile stresses with randomly occurring stress-raising discontinuities on the surface or in the body of the glass. If a large number of samples of nominally identical lights are tested to failure, there will be a significant variation in the measured failure strength. This means that glass strength must be addressed using statistical methods. So it's not a fact. It is more like a theory. It's going to be between, they have a set of numbers that it can be between. So it can be more, it can be less. It is generally accepted for weathered annealed glass that about 2/3 of the lights exposed to a uniform pressure will fail in the range of plus or minus 20 to 25% of the average breakage pressure for each size and thickness. For heat strengthened glass, the range is plus or minus 15%, and for fully tempered glass, it is plus or minus 10%. These percentages are termed coefficients of variation and are useful for the design of glass and prediction of the probability of breakage. The guidelines for selecting glass have gone through an evaluation since the early 1960s. In the 60s, thousands of lights of new annealed glass were tested to failure. The resulting data formed the basis for a set of empirical glass thickness selection charts, which were widely referenced by manufacturers, building codes, and standards up to and including the 90s. Additional research and testing of weathered glass and that was Additional research and testing of weathered glass that was begun in the 70s eventually led to a new set of glass thickness selection charts for annealed glass that were first presented in ASTM E1300. The glass thickness selection charts presented in ASTM E1300 standard practice for determining load resistance of glass in buildings have since become the acceptable basis for vertical and sloped glazing subjected to wind, snow, and self-weight loads. The ASTM glass thickness selection charts are based on the theoretical glass failure prediction model and the results of weathered glass tests. The ASTM charts incorporate detailed information relating to the effect of aspect ratio on the strength of glass. ASTME 1300 continues to evolve as more information becomes available. So it's all based on ratios and probability, not fact. The glass failure prediction model that serves as the basis for ASTME 1300 assumes that the probability of glass breakage is a function of the distribution and severity of stress raising surface discontinuities and the distribution of surface tensile stresses over the glass area. If the maximum stress level is two lights with different dimensions and thicknesses are the same, the light with the maximum stress over the greater area is more likely to fail. Again, if the maximum stress level in two lights with different dimensions and thicknesses are the same, so you have two different pieces of glass that are different sizes and thicknesses, but they have the same amount of maximum stress on them. The piece of glass with the maximum stress over the greater area is more likely to fail. It is more appropriate to base the structural adequacy of glass used in buildings solely on its modules of rupture as determined through the testing of small-scale laboratory specimens. So it is not appropriate to base the structural adequacy of glass used in buildings solely on its modules of rupture. The ASTME 1300 standard retained some concepts from earlier work, including the use of strength factors for heat strengthened, fully tempered, and insulating glass constructions. In addition, the ASTME 1300 standard introduced load share factors for insulating glass units that incorporate glass lights of the same and different thicknesses and types. ASTME 1300 also incorporates procedures to address the variation of glass strength with load duration using glass type factors for long and short durations. The load resistance factor for laminated glass depends on the relationship of the glass, dimensions and thickness, the layer, the interlayer temperature, and the load duration. There are currently seven charts utilizing four-sided simple support. Additional charts included for less than four sides. For laminated glass in ASTME 1300 standard, these charts are used to directly obtain the glass strength of laminated units. The use of factors for laminated glass strength are no longer applied as was practice in the past from the annealed monolithic charts. The only factors used for laminated glass in the current version of ASTME 1300 are for a change in glass type, heat strengthened, or fully tempered. Unlike most metal and other architectural materials, glass is usually designed on the basis of the acceptable probability of breakage or on the basis of historical experience and engineering judgment. ASTME 1300 presents general procedures to determine the load resistance of glass for the most common design probability of breakage of 8 lights per 1,000. In addition, an optional procedure is presented that allows other design probabilities to be addressed. Frequently, it is necessary to design glass of unusual shape and construction. In such cases, calculation techniques such as finite elements, finite differences, or standard in engineering mechanics formula can be used to determine the maximum principal tensile stress on the surface of the glass as a result of a specific load. ASTME 1300 presents conservative glass design stresses corresponding to a probability of breakage of 8 lights per 1000 and a load duration of 60 seconds per the 2000 and previous versions. Starting with the 2002 version of ASTME 1300, the load duration was changed to 3 seconds. So basically, in the early 2000s, they would put what they would think is a appropriate amount of stress on a piece of glass, hold it for a minute, and they found that out of every 1,000 pieces of glass, 8 would break based on those that specific load. In 2002, they changed it from 60 seconds to 3 seconds. These values were combined with statistical methods and the assumption that failure stresses are normally distributed to develop the glass design stress presented in Table 11. For different probabilities of breakage, a calculated maximum principal stress can then be compared to the values presented in Table 11 to conservatively estimate the probability of breakage. Table 11 presents probabilities of breakage ranging from 1 to 8 per 1000, while a probability of breakage of 8 lights per 1000 is common for vertical glazing. Designers and architects typically use a probability of breakage out of 1 light per 1000 for sloped glazing, skylights, and other critical applications. So the table 11 shows that out of 1 out of every 1,000, annealed glass had a specific breakage, heat strength had that specific breakage, and fully tempered had that specific breakage. Based on the instructions given before, we cannot assume that if it's annealed laminated glass that it would be this. There's a different table you have to look at for that specifically. Probabilities of breakage greater than 8 lights per 1000 are not generally recommended for the design of flat glass. The design stresses presented in Table 11 can be converted to 3-second duration design stresses by multiplying them by the load duration transformation factor of 1.21. In addition to strength, the deflection characteristics of the glass should also be examined by the designer, so how it bends. Deflections are a consideration in maintaining proper gasket engagements that are required to maintain continuous edge support of the glass. If the glass is wet glazed, excessive deflections can lead to improper sealant in performance. Specific issues relating to overall glass movement under design load conditions may affect placement of draperies blinds, or other shading devices. In certain circumstances, excessive glass deflections can become an aesthetic concern. In the evaluation of glass deflections, the designer should be aware that annealed, heat strengthened, and fully tempered glass share a common modulus of elasticity of 10.4 times 10 to the 6th power psi and a Poisson's ratio of 0.22, and therefore exhibit the same deflection characteristics under the same load. For a given glass size and load, a thicker glass is required to reduce deflection. ASTME 1300 presents methods for calculating deflections in glass with 1, 2, 3, and 4 sides of continuous support. For selection of relatively thick glass as used in viewing windows for large aquariums, glass railings, glass mullions, and animal enclosures, finite element analysis, finite difference analysis, or conventional engineering mechanics equations can be used to calculate stresses. Experience has shown that allowable stress ranges for such applications are as follows: annealed glass 600 to 1600 psi, heat strengthened glass 1200 to 3000 psi, fully tempered glass 2400 6000 psi. That is the allowable stress ranges on these glasses before they were to break. The suggested annealed glass design stresses are below the general accepted statistic fatigue limit for long-term loads, and the suggested design stresses for the kind of treated glasses are below the minimum requirement of the residual surface compression for these kinds of glass. The probabilities of breakage associated with these design stresses will be much smaller than 1 light per thousand. These same allowable stress ranges can be used in the design of structural glass railings and glass mullions supporting all glass walls.